recording has started. So, as far as review for the exam, we just went over all the logistics as far as the test is concerned and what, what's going to be on it and what it's going to look like. I didn't record that part, but I probably will later on, so if you want to look at it again. So, conservation of energy, right? First, we talked about energy, and energy was one of the first big concepts that we talked about in here. What was our definition of energy? What did we sort of use to define? Ben?
The ability to do damage.
The ability to do damage, or the ability to change things, the ability to make them different than they were before. Okay? Also, conservation, right? Conservation is an idea that shows up over and over and over again. Conservation of energy is the first time we ran across it in this class. When we talk about something being conserved, or the conservation of something, what does that mean in general? When we say this is conserved, or we talk about conservation of energy. Saved, or staying the same. So when we talk about conservation of energy, okay, specifically, conservation of energy, that means that any energy that we begin with, the initial amount of energy, has to equal the energy that we end up with, the final amount of energy. That's conservation of energy in general. Okay? One specific application of that we talked about was conservation of mechanical energy. First, mechanical energy. We remember what mechanical energy is. It is a buzzword. Emma, go ahead.
The sum of kinetic and gravitational potential.
The sum of kinetic and gravitational potential. There's also another one in there, elastic potential, but we didn't really talk too much about that. But mechanical energy is defined as kinetic energy plus potential energy gravitational plus potential energy elastic, right? And when we talk about conservation of mechanical energy, the idea of conservation doesn't change. We just apply it to mechanical energy. So, conservation of mechanical energy says that all of the mechanical energy that I started with has to be there at the end. MEI, initial mechanical energy, has to equal NEF, final mechanical energy. But we said that this only applies under certain conditions. What has to be true in order for us to see this? Another term that we discuss.
Conservative forces.
There can only be conservative forces acting on whatever it is that we talked about. Is that word somewhat familiar? So we said that only happens when there are conservative forces. And we said that there were two kinds of conservative forces.
Gravity.
Gravity's one of them, and that's the biggie. And then the other one, do you remember what the other one was?
Friction?
Not friction, definitely not friction.
Elasticity.
Elastic, springy stuff, right? Real quick, you said friction, right?
Yeah.
Why isn't friction a conservative force? What did we say that friction generally ends up doing? It usually causes heat, right? Is heat a form of energy?
Yes.
Yes. Is heat a form of mechanical energy? No. And that's why friction isn't a conservative force. Does that make sense?
Yeah.
When we talk about conservation of total energy, yeah, friction still converts, and it still conserves all energy. It turns like kinetic energy into heat, but that's not mechanical energy. That make sense? Was that good as far as reviewing that concept? Okay. Hopefully it comes back to you as we talk about questions relating to conservation of energy? If you go back and look at your tests, depending on which version of the test you had, there was a problem where there was like a squirrel. Let's see if I can draw a squirrel, probably not. It's got a big tail. I don't know, whatever. There was a squirrel
Is it floating?
that, no, because it fell out of the tree, right? And it asked you like, how fast was it going right before it hit the ground? So when it's in the tree, right, what kind of energy does it have when it's in the tree? Gravitational potential, right? And as it falls, what happens to its gravitational potential? It goes down, right? But what's happening as gravitational potential is going down? Kinetic is increasing, right? If gravity is the only force that acts on the squirrel as it falls from here to here, right? However much potential gravitational it starts with, all has to get converted into kinetic. But only if gravity is the only force that's acting on it. In real life, is gravity the only force that's acting on the squirrel as it falls out of the tree? No. You got like air resistance and stuff like that. But on a test, if it says neglecting air resistance, you can assume that whatever we started with here, you got to end up with here. Okay? Good there? All right. Any other energy questions before we move on to another topic that people have asked for? Good on energy so far? Okay. A lot of people asked about the mole stuff, so why don't we go there next? Okay. Let's go here. Let's go here. All right. So, up on the board right now is a copy of the quiz that goes along with your book for the section that relates to moles. Okay? This is like, you know, right from the publisher and stuff like that. Okay? I don't usually give you this quiz because a lot of times I think it's too easy. Okay? But as far as reviewing goes, I thought this might be a good thing for us to go. Now, I can't post this online, right? This is like copyrighted material from the publisher and stuff like that. Okay? What? No, I'd appreciate it if you did. All right. I'll use it to help you guys study, but you know, let's talk about it in terms of concepts and what we got. All right. So, first, there are some multiple choice questions up at the top. I will zoom in on the multiple choice questions. Okay. If you're watching on the video, you don't get the zoom, but let's go here. All right. So, question number one. Question number one says, Avogadro's constant is useful for counting atoms, counting large objects, both A and B, or none of the above. Avogadro's constant. Correct, go ahead.
Both A and B.
I'd probably not go both A and B. First, we got to identify Avogadro's constant. Do we remember what Avogadro's constant is?
No.
Okay.
6.14. 6.02.
All right. So, it's not avocado. Avocado.
That's a good way to remember.
All right. So, Avogadro's constant is 6.022 times 10 to the 23rd power. And we said that number was significant because this is the number of things that are in what? A mole of something. Okay? So there is always 6.022 times 10 to the 23rd things in one mole. Could we use it to count semi-trucks? You could, right? It's a lot of semi-trucks though, okay? So is this number useful for counting large objects?
No.
No. It's useful for counting small things because, like, what do we usually use it to count? Atoms, right? Not that there is only 6.022 times 10 to the 23rd atoms in 1 mole. There's 6.022 times 10 to the 23rd anything in 1 mole, but usually we use it for atoms because it's so small. Okay? Does that make sense as far as the answer to that question? Avogadro's constant is good for counting atoms because it's a big, big, big number. Does that make sense? Okay. All right. Next, question number 2. Question number 2 says, what is the molar mass of an element with an average atomic mass of 9.012 AMUs? Answer for this question is B. Well done, Willie. All right. So let's go back here. Okay. We learned that 6.022 times 10 to the 23rd atoms is equal to 1 mole. But we also discussed that if you have 6.022 times 10 to the 23rd atoms, you will have a specific mass. And that mass is equal to the average atomic mass of that element, but the unit on it is now grams. Where do we get the average atomic mass for an element? Where do you find it out? On the periodic table. Okay? So that decimal number, which is the average atomic mass, if you count out this many atoms, you'll get that number, but it'll be in grams. And we refer to that as, like in the question, what did they refer to that number as? The molar mass. Okay? This value here, we refer to as the molar mass. Because if 6.022 times 10 to the 23rd atoms is equal to 1 mole, and 6.022 times 10 to the 23rd atoms is also equal to this value, if A equals B and B equals C, right? What is that? Transitive property? I don't know, whatever. Right? That also means that 1 mole has to be equal to the average atomic mass in grams. And like we said, another name for this is the molar mass, because it's the mass of 1 mole. That makes sense? All this starting to come back a little bit? Kind of, maybe.
Can you read the question itself?
Sure. So going back to this question, right, you just got to kind of know the terms, right? So for 2, the molar mass of an element, if it has an average atomic mass of 9.012 AMUs, atomic mass units, its molar mass is going to be that same number, but in grams. Okay? All right. Good there? Okay. So, number 4. Let's jump down to number 4. What is the mass of 2.5 moles of calcium, which has a molar mass of 40 grams per mole? Okay? I probably wouldn't give you the fact that it has a molar mass of 40 grams per mole. I would say, what is the mass of 2.5 moles of calcium? So, now we start bringing some things together. Okay? If I take this, the mass of 2.5 moles of calcium. This is a conversion factor problem. So when we do conversion factor problems, what do we start off with?
Something over 1.
Something over 1. Okay, usually it's the thing that they gave you, right? So I'm going to start this problem with 2.5 moles of calcium, and then, like I said, if we want to, we can put that over 1, and that's fine. Okay? Conversion factor problem. This is what we started with. We said a conversion factor problem is just changing the unit of something, right? So, what do we do after this? We wrote our thing again. Rachel?
Don't you switch it to that 6.022 and
Not yet. Let's do process first, right? So, physically, what am I going to write down next? Go ahead.
times grams over
Let's do first. Let's just do this, right? Time sign fraction bar, yes? Okay, let's go there.
on the top grams.
Okay, on the top, grams. Okay. More specifically, grams of calcium. How do you know that goes on the top, Emily?
Because you're trying to convert it to mass and
Right. What is the mass? And we measure mass in grams, right? And then what has to go on the bottom of this conversion factor?
moles of calcium.
Why?
Because you want to cancel it out, so you put it diagonally.
Right. So we're trying to cancel that, right? So that's going to go on the bottom of our conversion factor. Units first. Okay? Now we've got our units set up, right? Now we got to put the numbers in. Where do we get the numbers from?
The grams is the average atomic mass of calcium.
These three things that we just wrote down is where we're going to get the numbers from, right? Whenever we see grams in a conversion factor, what number goes in front of it? Average atomic mass, right? Nico, what's the average atomic mass of calcium?
40.08.
Okay. 40.08 grams. And you got that number where, Nico? Periodic table, right? Whenever moles shows up in a conversion factor, what goes in front of moles? Just 1. Okay. Good there? All right. Next, what do we do? Cross multiply? Don't cross multiply. Right? Right? This is two fractions that we're just multiplying together. Right? So, we do 2.5 moles of calcium times 40.08 grams of calcium all over 1 times 1 mole of calcium. Right? You don't got to show me this step, right? This is just doing our math. But now we have one big fraction. In our one big fraction, units, what do we see units-wise? What unit shows up on the top and the bottom? Moles, right? So what do we do with that unit? It's gone. And then the only unit that we're left with is what? Grams. Now you just do your math. And this is pretty easy because there's only 1 on the bottom. Nico, did you run it through your calculator?
Yeah.
What'd you end up with?
100.2.
100.2 grams of calcium. Are we done with this problem? When we do this calculation, right, what's the last thing we have to take into consideration? Significant digits, right? Haley, when we do significant digits on a conversion problem, what do we have to do?
You have to the number of significant digits has to be the same as the number that we use for these numbers.
When we're doing conversion problems, we just make it match whatever we started with, right? So this is the number that we started with, right? Haley, how many significant digits in that number? 2, right? This is 2 significant digits, all right? So we come back down here. This is the answer that our calculator gave us. Is that 2 significant digits?
Yeah. That's 4.
That's 4 significant digits. So 1, there's a decimal point, but also 2. Nico, what do you see around these zeros, right?
1.
They're sandwiched, right? So that makes them significant. This is 4 significant digits, okay? This is a tricky one because of the numbers and the way they came out, okay? So, I would start off, this one's going to be significant, but I got to make this one significant too. Yes? Does that sound familiar? what's the only way I'm going to be able to do this one? I wouldn't give you one like this on the test. Scientific notation is the only way that we can really write this properly. Okay. Except for the end, that's a pretty standard kind of problem. Okay. On the test, this is a 3-point problem. 1 point for this part of the conversion factor, 1 point for this part of the conversion factor, 1 point for the answer. The answer is half a point for the number, half a point for the unit and significant digits. Good there? Want to do another one on your own? Please go ahead.
Wait, so if we didn't do significant digits, we would only get half one off?
2.5 out of 3.
Okay.
Yeah. Rachel, go ahead.
Okay, so then if you do that, we use the average time of, I don't even know what I'm saying.
Okay.
Alright, so 6.022, what do you use that for? If
What?
you're doing like
So-
conversions, like what question do you use that for?
Here, let's go back to this. Let's see if I can find one for you. 6.822, Rachel, is going to show up. If we go back to here, right? If we go back to these 3 things that we wrote down, these 3 equalities, right? 6.022 always shows up in front of atoms. Does that make sense?
Yeah.
So if I want to know how many atoms are in a sample, that's what I would use. If atom shows up in my conversion factor, then I would put 6.022 times 10 to the 23rd in front of it.
Right.
That make sense? All right, let's go here. You guys want to do another one? Just, all right. All right, let's go here. So this question says, what is the amount of nickel, which has an average atomic mass of 58.7 AMUs, present in 525 grams of nickel? So go ahead, start it off.
So are we saying how many atoms?
That's what this one's asking you for, okay? So, which is not really the best wording of this question, but I wouldn't ask it this way. I would say, how many atoms of nickel are present in 525 grams of nickel? So we start off, right, with whatever it is that they gave us, 525 grams of nickel. And then if you want, put that over 1. Time sign, fraction bar. You guys keep going. I'm just going to talk because I'm still recording, so I want to make sure we get it on there. So first, if we set up units, right? Grams of nickel should go on the bottom. And then atoms of nickel will go on the top. Because we're trying to get rid of grams, we're trying to go into atoms. That's what the question has asked us to do. Rachel, whenever atom shows up in a conversion factor, what number do we put in front of it?
6.022 times 10 to the 23rd.
6.022 times 10 to the 23rd atoms is how many atoms are in how many grams of nickel? What number goes in front of grams?
58.7.
58.7. Because, Beaver, what is that number?
The average atomic mass unit.
The average atomic mass, which we said is also sometimes called what when we turn it into grams? The molar mass, alright? So now, math-wise, right? Grams nickel on the top, grams nickel on the bottom. We cancel that unit out, and then we do a little math. That's what my calculator gave me, right? Am I writing that number down? Please don't write that number. You can write it down as long as you do something with it afterwards, right? How many significant digits does this number have to have? 3, because we started with 3. So 1, 2, 3. There's our 8. But what do we see after the 8? The 5, and especially after that 5 and 9, right? So we would round this to 5.39 times 10 to the 24th atoms of nickel. Good there? So tomorrow, bring me some questions, or I have more stuff for us to go over. Alright? Whatever works best for you. If you have questions, bring them to me. If not, I got stuff for us to do. Have a good day, everybody. See you tomorrow.